Hello and welcome to our webinar. Today we'll be looking at using remote sensing in potato production systems. My name is Janet Canters. I'm the editor of Spudsmart magazine and Spudsmart.com, and today I'll be serving as your moderator. First, I'd like to thank our sponsors, McCain Foods and BASF, for their support. I'd also like to note a few housekeeping items. This webinar is being recorded and will be made available on Spudsmart.com following the event. For audio quality purposes, all microphones have been muted with the exception of speakers. But we do welcome your input, so if you have a question or comment, please share it in the chat box on the bottom left of your side of your screen and let us know to whom your question is directed. Today we have two speakers who will talk about remote sensing in potatoes. Dr. Ann Smith, a research science with Agriculture and Agri-Food Canada in Lethbridge, and Brian Bohman, a Ph.D. candidate in the Water Resources Science program at the University of Minnesota. We'll start with Ann, who will explain what remote sensing is and take us through some of the platforms used and research that's been done. Then we'll hear from Brian, who will explain remote sensing for nitrogen management. So we're ready to go with our first speaker, Ann Smith. Go ahead, Ann.
Thank you very much, Janet. Oops. I went one too far. So good morning, everybody, and thank you for the opportunity to talk to you today about remote sensing in potato production. And when Janet asked me to talk about this, I kind of threw it back at her and asked, well, what do you want to know about remote sensing? So she kindly sent me a number of questions, and hopefully in the next 15 to 20 minutes I can answer at least some of those questions for you. So first off, what is remote sensing? Basically in remote sensing, we're acquiring data about a physical object without touching it, and we can do that in a number of ways. But traditionally in remote sensing, it would be something where we have an aircraft or we have a satellite where we're measuring the sun's reflectance coming back to that particular sensor, and that's called passive. And we do also have some active sensors where they actually send out a signal and we receive that signal back and we look at how much of the signal comes back. And so we're really exploiting the areas of reflectance in the visible spectrum, so the blue, the green, the red, in the near infrared. Sometimes we're doing some work with thermal, and that's becoming a little bit more interesting. And there's also some remote sensing done in terms of microwaves and radar, and Canada is actually a world leader in radar technology. They're about to launch a radar constellation with 3 different satellites that will monitor the Earth. So remote sensing, basically we're trying to exploit these differences in the signature of the reflectance characteristics from the sun. And what I have here is just a graph that shows you some of the spectral characteristics. So the green one here would be a typical vegetation. And so down here we have the visible, we have the near infrared, and we have the intermediate infrared. So if we look at the vegetation, the signature for vegetation is very different from soil. So here's my soil, and from water. So we're trying to exploit those differences. And one index that you may have heard a lot about is the normalized difference vegetation index, or the NDVI. And in that particular case, what we're doing is using the difference between the NIR here, which is high, and the red, which is low, and we're doing a ratio with that to give an estimation of the amount of plant material present. And if you look to the green, you can see that the green and the red and the near infrared change with the health of a leaf, with the amount of a leaf. So by exploiting this normalized difference index, we can look at differences in the health or the amount of vegetation. The NDVI is very widely used. There are many other indices available which are somewhat correlated to the NDVI, but maybe a little bit more sensitive to changes that are occurring. So in terms of acquiring the data, there's a number of different platforms that we can use. We can use satellite. We can use aircraft. The greatest one now is the UAV system. And then we can also mount some sensor systems on farm equipment. So in this particular case, they're putting up a microwave sensor and a green seeker. And one of the easiest ones probably in terms of remote sensing is to use your cell phone. And there are a number of applications out there in terms of using cell phones to identify diseases or factors that are affecting potatoes. This particular one is Buntata, which comes from Scotland, my home country. And they have a number of different things that you can do with that on a particular application. So there's a number of different sensors. The type of sensor you would want to use depends upon the amount of data, so the temporal sequence that you want for the data, the amount of detail that you want from the data, and also the cost of the particular sensor system. So here I just have some examples of imagery. So this one would be a satellite. It would be Landsat 7. You can make out the individual fields, but if you zoomed into that, you wouldn't see too much detail about the individual fields. We have Rapid Eye, which is 5 meter. These two here, if there's cloud cover, it precludes the acquisition of the data. So sometimes you may not get timely data with satellites. Then we have airborne. This one here is an airborne image that we got actually of a potato field. It's at 2 meter resolution, so you can see an awful lot more information in it. And then the bottom one here is a UAV image. So sometimes people call them drones. I call them unmanned aerial vehicles. It's imagery that's acquired with a red, green, blue camera. And it basically, the ground sampling distance is sampling in 11 centimeters. So you get a full wealth of information. And these two platforms are actually probably more flexible in the sense that you can fly when you want. You can fly under the clouds. And now some of the new sensors developed have instant light sensors, so they help us take care of cloud measurements. These particular systems don't go over as often. If cloud cover precludes it, then you may miss a temporal sequence and you may miss something in the imagery. Now there is potentially a game changer in the sense that Planet Labs has just launched a whole constellation of satellites. They call them nanosatellites, and I recently read that they have over 130 of these up there. They have launched some out of the space station. They've launched some out of rockets. The last series that were launched was 2017, and there were 88 satellites launched at the same time, and that's called a flock, and each individual satellite is called a dove. So there's potentially a lot of information. They all have a 4-band sensor, so a blue, green, red, near-infrared sensor. With the number of satellites we have the potential for daily coverage. And the spatial resolution, so the spatial distance they're measuring on the ground is about 3 meters. So depending on your application, you may well have the resolution that you require. So these just show you some pictures of the nanosatellite, and this is an image that I actually got for an area in New Brunswick that we're working on. In terms of the sensor systems that are present, there's a number of different ones. The ones I'm showing here are actually for unmanned aerial vehicles. They can be simple commercial-grade digital cameras. Some of them are adapted. Some of them are just typical red, green, blue. So just as you would take a photograph normally, that's what you get. Some of them are adapted, so maybe the blue band has gone and there's a filter put in there that you can register with near infrared as well. These are some of the newer systems, and I've used these two here, which are discrete bands. So they have very discrete images. This one has 5 bands in it. This one has 4. But the beauty of them is they have this instant light sensor. So as the UAV is crossing the field, it's capturing the instant light sensor every time it captures an image. And you can then calibrate the image based on the differential lighting conditions. There's a thermal image which measures canopy temperature, and we've actually just invested in one because we're kind of interested in whether stresses might induce an increase in canopy temperature, and can we see that earlier than any other visible symptoms. Hyperspectral and LiDAR we don't possess at the moment. Hyperspectral would be where instead of having broadband sensors, so like in the blue, the green, or the red, you have many, many different bands right across the spectrum. And some of the hyperspectral data that I've used in aircraft has 224 bands instead of just 3 or 4. So you can start targeting very specific parts of the spectra to look for very specific things. So So what can remote sensing do for you in agriculture? And one of the big questions I'm asked nowadays is, what will an unmanned aerial vehicle image do for me? And I think one of my concerns is that perhaps we oversell what the imagery can actually do. In this particular case here, these are remote sensing images. They're UAV images that were captured over a potato field July the 14th and July the 30th. And what I'd really like you to look at is in this little area where it's circled, you start to see something happening, but it's very obvious in the normalized difference vegetation index. So where we've looked at the ratio of the near-infrared reflectance to the red, you can start to see some things happening in here. So blue here would be high and the red here is low, and you can see this dot here. Now if I go in and we actually went out and looked at it, this area here was actually late blight, so it was a late blight in here. But this area here, the vegetation decreased because we have deer tracks in here. So I think I use this example quite a lot because I think it really shows that with limited number of bands, you can get some information, but we really can't tell exactly what's going on in that image. So the signature for late blight is the same as for the deer tracks. And I always go back to some information that was published in a journal a long time ago that basically said that with a limited number of bands, it's very difficult for us to separate the signatures for different stresses. We can tell something's going on, but for us to actually differentiate the different signatures is particularly difficult. So I think it's a very valuable tool in that it can direct you towards certain things, but it may not tell you the specifics of what's going on. I was very fortunate to be working on a project in New Brunswick, which was a little different for me because they don't have quite the sunny skies that we have in Alberta. But it was a collaborative project with Potatoes New Brunswick, McCain Foods, Agriculture Canada, the Eastern Soil and Water Conservation Centre, and grower cooperators. And what we were trying to do was develop new approaches to using remote sensing to identify limited zones of production in commercial potato fields. And because of the issues with cloud cover, the platform of choice was the drone or the unmanned aerial vehicle. There we go. The project ran from 2013 to 2017, and right now I've got stacks of data that we're trying to compile over the 4 or 5 years. But every year we would image about 16 to 20 commercial fields. We had 4 to 5 what we call priority fields, where we would set up sampling sites. So we'd set up 10 to 30 sampling sites. We would measure plant biophysical data and soil parameters, and that we'd measure that every time the imagery was acquired, and that would be 5 to 6 times in a season. And one other field that's very interesting, or there were 2 in 2006 that were intensively sampled, and these are actually things that I'm looking at right now because they contain a wealth of information. Over the course of the project, it somewhat evolved, and we went from digital camera, just a plain digital camera, to a multispectral camera with an instant light sensor, and that actually helped us in terms of reducing some of the issues with cloud cover. So here's just something from 2013. Here is just what we call a true color composite. This would be a false color composite. So this is just red, green, blue. This is near infrared red. And this is at 50 days after planting and 70 days after planting. And here are all our sampling points. And what we found was, if we looked at our sampling points 1 to 4 had low yield, and they also had very low vegetation indices. And we could zone our field based upon the low and the high productivity. And where we had low yields, we came out in the low zone of productivity based on the vegetation index. And where we had higher vegetation, we had higher yields. We couldn't differentiate between the medium and the high in terms of the yield. So it gave us some interesting information in terms of productivity and what we could do with the drone. Over the years, we've looked at the influence of vegetation and yield and how that relates to the information that we get out of the drone. So this would be our vegetation index. And you can see we get a nice relationship with the above ground biomass, but our relationship with yield is not quite so high. And I think there's a couple of things going on here. I think we're measuring above ground, things are going on underground. But the other question I had was that we go in there and we sample, but we sample small areas in the field. And perhaps we're just, with the variability, we're just not capturing everything that we want to capture. So I have gone back and looked at the intensively sampled field. And here we have a vegetation index that's derived from the UAV imagery. And the different colors represent the different levels of the vegetation index. So red is low vegetation, green would be higher vegetation. And here's all the sampling points we have. It was intensely sampled for soil sampling, there was electrical conductivity, and there was also a yield monitor. So if you remember this picture here, if we look at it, this is what came out of the soil electrical conductivity, and they've defined two management zones. And this management zone here we can see corresponds to the low values in the vegetation index. And down here we have some down here, but there's other low areas in here that are showing up with the vegetation index and not with the soil electrical conductivity. The one on the far right is the yield map. And so you can see where we have low yield here, there is an indication that we have a lower vegetation index. And down here we have lower yield and we have lower vegetation index. There's a lot more detail in the vegetation index than in the yield map, because here I'm looking at 9 centimeters spatial resolution and this one is 15 meter. But there's some similarities in the patterns that are emerging. This is if I take the RGB image that was there with the drone imagery, you can actually make out individual plants. And so if I go and look at a high and a low yielding, at this particular date, which is 55 days after planting, there's more plants in the high yielding than there is in the low yielding. And if I look at the amount of vegetation cover, so I've estimated how much plant there is to soil, there's 12% plant matter here, 23 to 80. You can see that at the higher yielding area, the plant canopy develops much quicker than it does with the lower canopy. And this just exemplifies it here, where I have high yielding would be the red, low yielding would be the blue. And you can see that the canopy cover, there seems to be some relationship between canopy cover and the ultimate yield. And there is actually a potato model out there that uses canopy canopy cover as an estimator in the prediction of yield. So that's some field scale. One of the other questions was, can remote sensing be used in potato breeding? And truly, the Scots are doing a lot of stuff with UAVs, and they're studying density and the health of the foliage in response to different parameters and to different lines, new lines that are forming. I am working currently with Dr. Jonathan Nielsen, who's with Agriculture Canada here in Lethbridge. He's a potato health. He does a lot of genetics work, but he's very interested in the interaction of the genome with the environment. So these genetic lines, how do they perform under different environments? They evaluate thousands of lines every year. So he's looking for a way to reduce the labor cost, to increase the number of replicates, and to measure things like vine metrics, growth rate, time to canopy closure, time to flowering, various things. He's also looking at tuber metrics. So we're actually building right now a system that would let us capture images in the greenhouse and look at these different lines and the growth potential. So one of the quick things that I did was I went and I took some digital imagery and I processed that through a different thing, like I transformed the color, and you can see here all the vegetation turns out really black. I can threshold, and I can make these nice vector layers, and I can calculate the areas of the plant. And over time, we can measure how much that plant grows, and we can look at the genetics and how that influences the growth rate. We're also looking at some tuber quality. Jonathan's very interested in sugar ends, and whether we could use a non-destructive method prior to frying to come up with an estimate of whether we have sugar ends or not. So this was just an experiment we did with a field spectroradiometer, and we're looking at particular features in the spectra to see whether we can differentiate sugar ends from non-sugar ends. So in terms of remote sensing and potato production, I think there's a number of areas that we can contribute. In terms of a lot of interest in UAVs right now, I think it's a valuable scouting tool. It can direct sampling. You can take it over time and look for areas that are changing. We can look at variability and see whether some of the differences in yield relate to inherent parameters in the soil. From what we're looking at right now, it seems that if we get early images of UAV images and we calculate the vegetation index, it does relate to yield. And we're looking at satellite imagery and how that can actually help in potato production. And the area that's also of interest is in trying to fast track some of these new genetic materials and evaluate them under a number of different conditions. Ultimately, using remote sensing in potato production will depend on what your application is and also on the economics of the system and whether the system for your particular case is economic. So with that, I believe I used up my 20 minutes. So thank you very much.
Thank you very much, Anne. That was excellent. If anyone has questions for Anne, please type them in the chat box onto the bottom left and indicate what your question is and if it's for Anne. Our presenters both of our presenters will have a chance to answer them at the end of the next presentation. So now we're going to go on to Brian. Take it away, Brian.
All right, hello everyone. I'm really excited to be talking with you today. My background in remote sensing, I just want to go over 3 things before I start my formal presentation that I was thinking about while Anne was talking. And one of them is my bias, and 2 of them are 2 comments I've heard over the past year. So I'll start with the comments I heard from potato producers. I've been involved in a series of workshops in central Minnesota, hearing from potato producers, among other producers, about things they're excited about for the future. And one of them is remote sensing. And one of the sentiments we've heard throughout these meetings is, producers want plants that talk, some plants that give them information, that can give them something they can do about the information remote sensing is giving them. So I think keeping in mind we want plants that talk is something important. I was also a participant at a remote sensing conference in Madison, Wisconsin last fall, and we talked about lots of things that remote sensing can do, from breeding to disease detection to nutrients. And one of the producer groups in attendance, they were talking about the available remote sensing platforms, and they gave basically the pointed comment, we're receiving lots of colorful maps, but they don't mean much. And I think that's true. We might have oversold some of what remote sensing can do. And for my own bias, my introduction into remote sensing and potato production was really I was using it to schedule fertilizer applications in my research, which I'll be going into. But my bias really is that we need to have tools that can tell us something to do. We need actionable information. So a lot of what I'm going to be talking about today is how do we take remote sensing and turn it into actionable information for nitrogen management. So taking a step back, I put together this slide for a non-academic, non-agricultural audience to try and really get at what we're doing with remote sensing. And I use the metaphor of jelly beans and kids. And so you can think about jelly beans as your nutrients, whether it's nitrogen or water in some cases, if you're trying to use remote sensing to manage for water. And the plants, in many cases, are kids that are hungry, that are looking for jelly beans. They have their own favorite flavors too. So they might be looking into that jar and deciding, I only want to eat the red ones, or I only want to eat the blue ones. Well, as a parent or as someone who's watching over this field of jelly beans and kids, we have only a couple of methods we can use to determine what has been consumed and what the needs are. We can either use direct estimation, which would be counting out the jelly beans one at a time. That's direct tissue sampling or plant sampling or soil sampling. We can use things like physical observations. If you see a kid passed out on a pile of candy, it's a good sign that there's been, way too much sugar eaten. We can see visible symptoms in the field in some cases through scouting or other methods. But then we also have a tool like indirect estimation. Take a sample of the jelly beans, weigh them out, and then count how many are in each, and we can use that to make a better estimate of the whole status. And this is kind of the bucket remote sensing falls into, is this indirect estimate. So we can look over a whole field and make a status assessment of what's available, what's been taken up, and what can we do to manage to make sure we get our maximum yield, and we get them in colorful maps in many cases. So I'm echoing a little bit what Ann said, but I'm going to be taking more of a nitrogen-specific approach. So this is from a UAV image over the research study that I conducted over the last 2 years. And we can see this is a study of 6 different nitrogen rates. All the nitrogen rates are in these smaller plots. The 2 bigger plots are irrigation rates. I'm not going to talk about that much, and they didn't cause much of a difference. But you can see differences in greenness and canopy cover between some of these treatments. Like this is our control rate treatment. We have some intermediate nitrogen rates at about 180 kilograms of N per hectare, and then we had higher nitrogen rates of 270 kilograms N per hectare. And you can make out some of the differences in some of the plots, but what we can use remote sensing for is to really help us differentiate what differences are we observing. So again, how does remote sensing work? We're using these differences in reflectance between the soil and the potato to make inferences into, say, crop nitrogen status. And so the image Ann showed before was just looking at a generalized vegetation curve versus generalized soil. What we see here is this is hyperspectral imagery of low N status potato, which is the curve where you have the higher reflectance. You can see these 2 different patterns between the high N here and then the low N here. And so we can use these characteristic patterns of how the green reflectance, the red reflectance, and the near-infrared reflectance to make an assessment of how much nitrogen is in the plants and then how much canopy cover there is too. Moving on, echoing again what Ann said a little bit, most of our remote sensing platforms that we have that are available are 4-band remote sensing, where you have these broader bands in the blue, the green, the red, and the near infrared. And they kind of take large portions of the spectrum and bucket them together, which is different from when you have all of these small, narrow bands, a multispectral or a hyperspectral. And so what we actually have been using in our research is a multispectral platform. It's called the CropScan. It's ground-based, and so you can take this out into the field. It can also be tractor-mounted too for scouting. And it takes point images, and we have 16 bands in the blue, green, red, the red edge, and the near-infrared that we're able to use to make more of a targeted inference into the crop nitrogen status. So when I think about what remote sensing can tell us, at least for managing nitrogen, there's 2 things. One is the canopy cover percentage. How much soil is visible? That's really easy to do using an index like NDVI. It's geared towards identifying how much soil and how much vegetation is there. This is a really strong signal, and there's lots of things that can affect the canopy cover percentage, how much soil is visible, but remote sensing is easily able to detect this. So this is data from another study looking at the whole field scale, taking satellite images of a potato field, and you can see the greener colors are more full canopy cover, where the yellow and brown covers are low canopy cover like soil. You can see that there's patterns over the growing season, both through just the period of crop development, and then perhaps there's some soil differences or disease or whatever might be causing the differences, and then again at the end of the season, the senescence. So we can use remote sensing to tell us what the canopy cover percentage is. We can also use remote sensing to tell us what the vine nitrogen concentration is. How green are the vines? And this is really important because the amount of nitrogen in the vines controls how much chlorophyll there is, which controls how much radiation can be used through photosynthesis to build plant biomass. Green is good, although in potato we can have a problem where too much nitrogen in the vines can cause excessive vine growth, which can actually decrease your yield. So again, we have lots of good data. This is another study on a field scale looking at a whole field, and we can detect through an index like the green ratio vegetation index how much nitrogen is above ground. But what remote sensing can't do directly is we can't directly predict tuber yield. We're not observing the tubers themselves with remote sensing. We're observing other things that could indicate what the tuber yield might be. So things like, you know, one of the things Anne said later in her presentation was she observed that early canopy cover, in areas where the canopy cover developed sooner, there was greater yield. Well, that makes sense. More canopy cover sooner means more intercepted radiation, which means more accumulated biomass. So we can use those things as signals to tell us things like tuber yield, but when we're remote sensing, we're not actually sensing tubers themselves. And we can't also directly estimate biomass for the same reason, because the tubers are underground, and the canopy structure of potato, with the vines the way they are, is different than other grain crops like wheat or maize. It's just the way that the potato plant is above ground makes it very difficult to estimate biomass, whereas in other crops that's easier to do. So I just want to point those two things out. It's very difficult to predict tuber yield and directly estimate biomass from remote sensing. So I want to show some of the vegetation indices that we were using, or we have been using, in addition to NDVI. So vegetation index just uses differences in reflectance at different wavelengths. So for NDVI, like Anne pointed out, we're looking at what is the reflectance in the near infrared region compared to the reflectance in the red region. And when you have soil or when you have lower canopy or lower canopy cover, you're going to see differences in the NDVI. We can also use indexes like the green ratio vegetation index. You can see that for NDVI, the low N and high N had very similar red reflectance, but they had different near IR reflectance. For GRVI, the green ratio vegetation index, we're using the green bands and the near infrared. And you can see when there's low N and high N, there's differences in the reflectance of green, which we can use. We can turn that into useful information. There's another index that I like to use called Simple Ratio 8. It combines the green, the red, and the near infrared all together. And these three indices I've mentioned so far, these are broadband indices. They can be done on existing UAV and satellite platforms that have the green, red, blue, green, red, and near IR bands. But this index, the Marist Terrestrial Chlorophyll Index, this is what we actually have been using to schedule nitrogen applications for potato. This is a narrowband index, and it's looking at the red edge, and the near IR. And when we're able to zoom in very specifically on this red edge region of the spectrum, we can get a lot more information than perhaps a broadband index. Although there are trade-offs. The more bands you have, the more difficult these images can be to handle, and the platforms themselves can be more expensive. So what is our ongoing work then? We just completed a variable rate nitrogen field study last year, and I'll be going over the results of that and the methods we use. And I've also recently been working on new methods to determine crop nitrogen status from remote sensing. This is an area of ongoing work, and we're trying to connect insights from other crops like wheat or maize and adapt them to the unique conditions of potato. So for our field study, we had two objectives that we were trying to accomplish. We wanted to utilize remote sensing to determine the need for in-season variable rate nitrogen fertilizer applications. So can we, in the middle of the season, the same way you might use petioles to determine how much nitrogen you're going to apply or when you're going to apply nitrogen, can we use remote sensing in a similar way? And then we also wanted to assess the yield outcomes. If we're using variable rate nitrogen based on remote sensing, does it affect our yields? So those are the two objectives of our study. So jumping right into the results, what you're looking at in this figure is a graph of the MTCI, that was the narrow band index, over time, over the growing season. So the arrows show our 4 scheduled fertilizer application dates. We're comparing a variable rate treatment to a controlled release treatment and a scheduled split application treatment, where on these 4 dates we had scheduled via fertigation an application of 22 kilograms N per hectare of UAN. Now we can compare the variable rate plots to the control, not the control plots, but this is our well-fertilized reference. So we compare the index value from our variable rate plots to our reference plots, which is shown in the gray. And if the X falls outside of the gray zone, then it's a good suggestion that we should apply fertilizer. This method doesn't tell us exactly how much fertilizer to apply, but it can give us an indication that a fertilizer application may be necessary. And so in this case, we reduced nitrogen applications by 22 kilograms N per hectare in 2016. In 2017, we were able to detect on 2 dates the need to apply fertilizer compared to the 4 dates that were scheduled. And so we were able to reduce the N rate by 44 kilograms N per hectare. Now, in both of these, you can see that the variable rate treatment is very close to the other comparable 270 kilogram N per hectare treatments, although it does drop off at the end of the season. The control treatment, where we only applied 45 kilograms N at planting in the form of DAP, you can see marked differences throughout most of the growing season. So this is a sign of severe N stress. And we don't want to be down here. We want to stay as close as we can to our well-fertilized reference without over-applying fertilizer. So what we found was that, using this variable rate treatment, we could reduce our nitrogen rate by 22 to 44 kilograms N per hectare, which is an 8 to 16% decrease compared to our 270 split, which is the reference. And there was no significant differences in yield between this variable rate and this conventional treatment. They were very similar. But what you need in this case to make it work is you need a reference strip. And although this method might work very well on a plot scale, there's challenges in making it work at a production scale. We want to find a method that doesn't necessarily require a reference strip to work. So that's where the next part of this research comes in. So how can we take an image of plots or of a field and use these indices I've identified to do something that doesn't require a reference strip? Well, we know that indices like the GRBI, the SR8, the MTCI are closely related to vine end concentration, and we know that indices like NDVI are closely related to canopy cover. And let's take a look at a graph that shows that. So 2 figures. You've already seen the one on the left. This is showing the MTCI value from 2017. So basically, this is giving us a sense of the vine nitrogen concentration. And on the right, you have a picture of an NDVI. And you see that it quickly increases and then is fairly uniform over most of the growing season. Now, these are taken from the same plots. They have the same treatments, and there's a lot different information being shown from the MTCI and the NDVI. You can see in the NDVI, even the control treatment, low nitrogen, only 45 kilograms N, it still has a very relatively high NDVI value. Whereas if you're looking at the vine end concentration, the MTCI index, it's much lower. So we want to try and take advantage of that. So again, just looking at this data in a different way. Some indices, like the MTCI, they show a strong linear relationship. It's not perfect, but a good linear relationship with measured vine nitrogen concentration, while other indices like NDVI, the relationship just isn't quite there. Now, we're working on a process of how do you combine the information from NDVI that tells us canopy cover, and that combines the information from something like MTCI, which tells us vine nitrogen concentration, to make determinations on how much fertilizer to apply and not just when to apply fertilizer. So we're working on algorithms, we're working on models that can put these indices, put this information together in a way that is calibrated and validated, that we can predict accurately what the vine nitrogen concentration is. And you can see so far we've developed a pretty good relationship of an R-squared of almost 0.9, where we can use remote sensing to predict what the vine nitrogen concentration is going to be. Now our hope is to use this in a similar way to how you would use petioles in a field. When you take petiole samples, you have a sufficiency range for a given day of the growing season. We're hoping to be able to do the same with remote sensing. And this is an area of work that is very much ongoing. So just to summarize our findings, we're finding that a combination of indices like SRH, GRVI, MTCI, and NDVI could accurately predict our vine nitrogen concentration. And we're hoping that a method like this could be used instead of petioles or another method to, like scheduling your nitrogen applications, to determine nitrogen status, and it would not require a reference strip. So with that, that's what I have prepared, so I think we'll turn it over to questions.
Great. Thanks very much, Brian. A great job by both our speakers. I'm just going to switch this across to this one. I'd like to invite everybody, of course, to ask questions of the speakers by typing in your question in the chat box on the bottom left side of your screen. In the meantime, I have a couple questions here. I'll start with Anne. So it's a very basic question. You know, what are some of the benefits of using remote sensing?
Okay. In terms of remote sensing, I think at the field level, there are maybe two categories we could lump them into. If you have UAV imagery where you have high resolution, then I think you can use it as it provides an overview of your field, and it will help you in terms of scouting for areas where you have lower productivity. So it kind of gives you an overview of your whole field, and you can start to look for things that are happening. You could use it in terms of monitoring, so you get images over time, and I think that's where the beauty of remote sensing comes, is that if you can keep getting temporal information, you can look at changes over time. So where you might have developing areas that are lower yielding than higher yielding. If I look back to the work that we're doing with the field study, it's almost like you have to go back. You have to go backwards before you can go forward. So I'm looking at the yield data and what's telling me, like what does the image tell me in terms of the yield data? So there are certain areas where the soil is a parameter, so there's an inherent factor in the soil. But there's other areas where it looks like my vegetation index was low, but my yield was high, and vice versa. So then I'm trying to look at, well, what's going on there? Is it I have less number of plants that are germinating, or what are the issues there? So I think it can be used in a lot of different ways. I think right now we're maybe at the point where it's a scouting tool, and it can be monitored. You can use it for monitoring. I guess like Brian, I'm a little bit concerned that we oversell what we can do with remote sensing, because with a 4-band sensor, there's a limited amount of information you can get. You know that the amount of chlorophyll per unit area is changing, but is that due to lower biomass, or is that due to a decrease in nitrogen?
Right. Okay. Brian, a question for you is why is it important for growers to monitor their nitrogen rates and applications in potato production?
So I think one of the things to keep in mind is when you under-fertilize, you have your nitrogen stress, and that decreases your yield. But at the same time, there's plenty of research that shows that over-fertilization can lead to excessive vine growth and actually decrease your yield, decrease your harvest index. So getting it just right, making sure you're getting exactly the right amount of fertilizer, nitrogen fertilizer, to the potato plant, and that could vary over the field. The optimum rate in one part of your field could be different than the optimum rate in another part. That's really important to maximize your yield. There are the environmental concerns too, but I think one of the things that I'm becoming more drawn to as a motivation to do this work is that there's as much of a penalty for over-fertilization in certain conditions as there might be for under-fertilizations, and that's just inherent in the potato production system.
Sure. Another question, Brian. If you want to ameliorate poor moisture or nutrient conditions, can a grower integrate this information system with a delivery system on the machinery for the product targeted application on a limited spot basis? It's a long question.
Well, I think what the question is getting at is, could you use something like variable rate irrigation or a sprayer or an applicator that's got variable rate nozzle, something like that? Of course. You need to make sure that the information you're collecting is georeferenced, meaning you take the picture and then it has a GPS attached to it so it knows exactly where in the field this is. That's one of the things that I'm becoming especially interested in, is how do you take this remote sensing information and then create variable rate applications over the field using the spatial information. So it's definitely possible, but there's lots of hoops to jump through. One of the hoops is, how do we make information out of the remote sensing data? And then the other one is, how do we actually logistically make that application possible? And the first part of that, the information, is going to come from researchers and a little bit from industry. And the second part, I think, is going to come primarily from industry and figuring out how do you get the information into the equipment and then make the applications happen.
Yeah. Okay. Anne, I have a question here for you. Did you have any, when you were doing your research, did you have any success determining sugar ends without frying them, or is that still ongoing research?
The work is actually ongoing. We tried a couple of things just to see how it would work. We were developing the protocol. We were going to do some more work on it. One of my concerns is that we used a spectroradiometer, so it gave us this whole spectra that we could look at, but it only measures a very small portion of the potato. So the question is, did we hit it correctly or not in terms of looking for the sugar end, because it was a transition down the French fry or the chip. Now, I have a colleague at the University of Lethbridge who actually has an imaging system that will go all the way up to the shortwave infrared. So we would like to use the imaging system because we think there's a transition going down the tuber. So if we don't hit it right at the right spot with the radiometer, we may have missed something. So the work is ongoing, and it's something that we're going to try a few different things to see if we can get some more answers.
Okay. Another question is, instead of a reference strip, can you use PDO samples to truth it?
That's one of the things we're looking at. I don't know if it's as straightforward as using petioles, because it's when we have a reference strip, it's related to the rate of nitrogen that was applied, whereas the petioles are an indicator of the crop nitrogen status. So I think it could be possible. It's not something that we've fully worked out yet, but that's something that for all of the studies that we have, the remote sensing information, we also have petiole samples too, and in some cases whole plant samples of nitrogen content. So we're trying to figure out, growers in many cases are used to taking the petiole samples in the season, getting that information turned around relatively quickly and making decisions based on that. So is there a way that we can take advantage of the sampling that's already being done and put it to further use with remote sensing? I would hope so, but we haven't figured out the nuance of that yet. But I would say it's likely that that's possible.
Okay. Another question.
Can I just add a little bit to that? That
You
I
bet.
know that they have done some work on that in New Brunswick, I believe. And one of the problems that you have is that the petiole is kind of like the here and now, and the image is like the accumulation of nitrogen over time. So what you see in the image is the accumulation of the nitrogen status over time, whereas the petiole might be what's happening there and then. So I sure hope we can do it, but
yeah. Okay, Brian, are you able to give absolute values of the nitrogen content of the crop? Did we see that?
So that's what we're trying to develop, and it's not. We have the relationship to whole plant nitrogen content is not as strong as the relationship to vine nitrogen concentration. And that's an important distinction to make. The vine nitrogen concentration really means how green is the above ground biomass. The whole plant nitrogen content, that takes into account how much matter is in the vines, how much matter is in the tubers, and how much nitrogen is in both of them. Our relationship starts to fall off when we look at whole plant nitrogen content the quantity, the mass of nitrogen. But when we look at vine nitrogen concentration, we're developing a method that can accurately predict what the absolute vine nitrogen concentration is. Now, I do have to preface that a lot of this work is still preliminary. We're doing another field study this summer to validate some of our initial findings, but that's where we're moving towards, is turning the remote sensing indices into an absolute measurement of nitrogen concentration in the vines that could be used for management.
Okay. So here's a question for either or both of you. You can both comment on this one. We've heard that drones have advantages in terms of perhaps better resolution than satellite data, but are a lot of work in many ways. Among other disadvantages, what are the disadvantages and advantages of both?
Brian, do you want to go or you want me to go?
Why don't you go first and then I can follow up?
Okay. Okay, so I guess there's advantages and disadvantages to both. I think in terms of satellites, we perhaps didn't have the spatial resolution to look at the detail that you want in a field, and that cloud cover was a concern. Now, with this Planet Labs coming online, I don't know if that's going to be a game changer in the sense that they can image every part of the Earth every day, so potentially you could get the imagery when you want it. What the cost of that imagery will be may dictate whether it's usable or not. In terms of UAVs, I think they are more flexible and you can get more information from them. They are a lot of work in terms of piecing together the individual images, but as time goes on, I think it's getting easier to do that. So it's kind of hard to tell which one's going to win out in the end. I think the bottom line is whichever one will actually be cheaper is probably the one that's going to win out.
I would echo what Anne has said. What I would add is that I agree that the Planet Labs could be a game changer when you have daily return times. Doesn't matter if it's cloudy, because hopefully one day out of a week you're going to have enough or low enough cloud cover where you could actually get a usable image. One of the major problems with satellites before was the return time was so infrequent that maybe you had once every 2 weeks, and then if it was cloudy on that day, then that image was not useful. For the UAV images, I think the resolution provided, at least for managing nitrogen from low-flying drones, say sub-meter or even centimeter accuracy, isn't all that useful. It might be useful early in the growing season, but when we're trying to detect canopy cover and detect vine nitrogen concentration, we don't need that great of resolution. On a meter scale would be just fine. And that's because the canopy in potatoes, it closes relatively soon in the growing season and then stays at that constant full cover level. So I have colleagues who are working in maize systems, and they're making their nitrogen decisions at, say, V4, V6. And so at that point, you need to differentiate the leaf from the soil pixels to get the most information. In potato, especially in irrigated systems, because we're able to manage that nitrogen during the period where we have full canopy cover, we don't need the same type of resolution. So the type of platform used might even vary between cropping systems, and this is something that we're still trying to piece together. What is the most effective way to get this done? I will also add that aerial imagery, from what I understand, is up and coming, and I think aerial might actually be a good combination of the benefits of UAVs and of satellites, the flexibility, but also some of the stability of satellites.
Okay. Anne, do you know if any research has been done on the cost-benefit analysis or return on investment when using remote sensing platforms?
I think there's a lot of interest in that. There's a lot of questions about whether it's profitable or not. And I actually just I was reading it this morning. There's a new paper coming out about unmanned aircraft systems and the economics. And part of the problem is that in a lot of the economic studies, they haven't used the same method. And so it seems to be highly variable, whether it's profitable or not. So I think there's limited information in terms of the economics of remote sensing. and a lot of it will depend on where you are, what your problems are, and I guess probably the end point would be the return, like what the crop's worth in the end.
Mm-hmm.
So to answer your question, I think there are some economic studies out there, but they're not very consistent.
Yeah, I think that probably will improve or increase, I guess, as the popularity and perhaps the lowered costs, hopefully, for producers comes about, for producers and anybody in the industry. Somebody will get it in their head to do a study more often.
Can I add in something on this real quick?
You bet. Yeah.
So in our study, we were doing kind of a crude economic analysis, and what it comes down to is, in our case, we were able to reduce nitrogen fertilizer by 20 to 40 kilograms per hectare. Now, is that decrease in input cost going to offset the increase in management or other expenses related to remote sensing? I don't know. I don't know. At least from a labor standpoint, the method we used is pretty labor intensive, both in the collecting of the samples and in the processing time. I don't know if that pays off. There is potentially an environmental benefit by reducing your nitrogen rate. I don't know if it pays out in the economic sense, at least right now.
Okay. One final question I'd like both of you to take a stab at, and that is, what advice would you give to potato growers who are considering looking at remote sensing to assist in their production systems? Start with Anne.
Start with me. I guess I'm a bit more conservative by nature, so I would think start small. Maybe you can buy drones relatively cheaply, so perhaps maybe getting your own drone and flying some of your fields and seeing if you see any benefit towards using it, whether it's good for scouting or over time. It tells you some areas of the field where things are changing. So I think that would probably be the route I would go right to start with, is just get some imagery and see whether you actually see anything useful in it.
Okay. And Brian?
I would say that the two things that I would say are useful from remote sensing, and echoing what I said before, is remote sensing right now for potato production is able to assess your canopy cover, and it's also able to assess your vine nitrogen concentration. Those are the two things. And until we can find new ways to interpret the spectral information or have new indices or some other new tools, most of what you're seeing on the market right now that's commercially available or that a producer could do themselves is really going to relate back to canopy cover and vine nitrogen concentration. And I think by remembering that that's what the remote sensing image is telling you, it grounds us from overselling the potential and reminds us what information are we actually gaining.
Okay. Anything to add from either of you? If you have any words of wisdom for a last comment?
No,
Anne, do you have anything to add?
I'd just like to thank you for letting me participate in this, and if anybody has any questions or has more information they seek, then just feel free to contact me.
And Brian?
The same for me too. Thank you very much.
Thank you both very much. And on the screen right now, you'll see the email addresses of both of our speakers. If you have any questions, I believe both of them are open to answering them via email. So quickly jot those down if you could. I'd like to thank both Anne and Brian for making time in their busy schedules to share their insight and expertise. I hope everyone who's listening in has found the information valuable. I'd also like to thank our sponsors today, BASF and McCain, for their support. So the presentation will be made available online at spudsmart.com early next week. So this presentation, you were able to go to our website and review it again or view it again. And thanks for your attention today. And on behalf of the team at Spudsmart, we hope you have a great rest of your day. Bye-bye.